Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. In this episode, we'll discuss using power series to compute various quantities. Power series are polynomials, and using polynomials is often easier than using other functions to perform computations. Polynomials are easy to integrate and differentiate, and we can play various games with Taylor series and power series polynomials. When we have a difficult math problem, often we like to replace the problem by a similar nearby problem, and that nearby problem may be easier to solve than the original problem, and as long as we know the solution will be very close to the original solution, we can be comfortable doing that. To recall, power series are infinite polynomials, sum of a coefficient times x minus a. A is the location where the power series is centered, to the power n, and we have an infinite number of these terms. Power series converge when the ratio of the new terms over the old terms is less than or equal to 1. And if it's equal to 1, we have to carefully check about that convergence. But when the ratio rho is less than 1, we have convergence. Power series converge either only at x equal a, where it's centered, or for all x, or on a symmetric interval around a. Taylor series are used to approximate a function by a truncated power series, matching the function value and the derivatives at a point. So, for example, the fifth Taylor polynomial, p sub 5, would match the function value as well as the first 5 derivatives of the function at the point x equal a. If we use n terms, or Pn, n terms of the power series, then we have an estimate for the remainder, or an upper bound for the remainder, that has to do with the n plus first derivative of the function, and there's division by an n plus 1 factorial, and times how far you are from the center point raised to the n plus first power. So that's the remainder term, and on the left we have the truncated power series. Let's consider an example. Suppose we want to find the fourth Taylor polynomial, p sub 4 of x, for the function f of x equal e to the x squared. And we're going to find that Taylor polynomial around x equals 0. Well, what we could do is we could use the definition of the Taylor polynomial. Consider the function value, f of x is e to the x squared. Consider the first derivative, the second derivative, the third derivative, and the fourth derivative. And as we can see, that gets messier and messier as we move along. We would plug in x equals 0 into each of these and plug into the formula for the Taylor series. And we would get 1, f of 0 is 1, f prime of 0 is 0, f double prime of 0 is 2, f triple prime of 0 is 0. The fourth derivative of f at x equals 0 is 12. And we just plug into the Taylor series formula, and we get 1 plus x squared plus x to the fourth over 2. Now that takes a little while to do because we have to find so many derivatives. One of the tricks we can play with power series is that we could consider the power series for e to the x, which is one of the half dozen or so that you should know, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And therefore, e to the x squared, well, for that, we just need to replace x by x squared in each of these terms. So we get 1 plus x squared squared over 2 factorial, and so on. Well, that gives us all we need to get to p4 of x. So we end up with p4 of x is 1 plus x squared plus x to the fourth over 2. We get the same answer, but it's much more streamlined. Let's consider another example. If we want to evaluate a limit, in this case a limit as x goes to 0 of natural log of 1 plus x minus x plus x squared over 2 all over x cubed, well, there are a couple ways to do it. Let's consider using power series and Taylor series in order to solve this problem. We can recall that one of the series that we know, or should know, the expansion for is 1 over 1 minus x, which is 1 plus x squared plus x cubed plus dot, dot, dot. And therefore, if we replace the x by minus x, that gives us 1 minus negative x, or 1 plus x. And on the right-hand side, we just need to replace the x's by negative x. Therefore, getting 1 minus x plus x squared minus x cubed, and so forth. If we integrate both sides, we get natural log of 1 plus x on the left. And on the right, we get x minus x squared over 2 plus x cubed over 3 minus dot, dot, dot. We do have to be concerned about a constant of integration, which in this case, the constant of integration, if we plugged in x equals 0, we will find the constant of integration is 0. So we can expand the natural log of 1 plus x by x minus x squared over 2 plus x cubed over 3, and we can plug it in up at the top. So let's go back to our problem. We can now consider this limit by substituting the power series that we just found. And we can take those terms, we subtract off the x, and then we add the x squared over 2. And we notice we get cancellation, x minus x, x squared over 2 minus x squared over 2. And we're left with x cubed over 3 plus terms that have higher powers in x, such that those terms, as x goes to 0, those go to 0. The x cubes cancel, and we just get a third. Another way to solve this problem is to use 3 steps of L'Hopital's rule. You have to take 3 derivatives in that case, and that might be considered somewhat messier. Let's do one last example concerning tricks that we can deal with power series and Taylor polynomials. We could ask which Taylor polynomial for sine x gives sine of 0.2 radians to within 10 to the minus 8th. Well, we should know the power series for sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so forth. We could use the standard remainder term over here on the right, computing the derivatives of sine x, which are pretty easy, and those derivatives are never bigger than 1. So it's really not a difficult way to do it. Or we could consider that this series for x equal 0.2 is an alternating decreasing series. So we can note that for an alternating decreasing series, the error term is no more than the first term that's omitted. It's no more than the first term that is omitted. So we consider the value of the various terms. The x cubed over 3 factorial is about 0.001. The x to the 5th over 5 factorial term, when x is 0.2, gives us about 2.66 times 10 to the minus 6th. And the x to the 7th term gives us 2.54 times 10 to the minus 9. Therefore, the term through the 5th power will give us an error of less than 10 to the minus 8th. So to compute sine of 0.2, we can get a very good estimate using 0.2 plus 0.2 cubed over 3 factorial plus 0.2 to the 5th over 5 factorial. And we know that that answer will be within 10 to the minus 8th of the exact answer. Let's have a moment of math culture. There were 3 mathematicians that were somewhat religious, and one day they got together after services and they were talking, and one of the mathematicians asked, well, how do you decide how much to contribute to charity, to give to God? And one of the other mathematicians says, well, it's easy. I take a giant compass and I sketch a circle on the ground with a diameter of about 4 feet. I then take all my money and I throw it up in the air, and all that lands inside the circle is mine, and all that lands outside the circle I give away to God. What do you do? That mathematician asked. Well, one of the other mathematicians says, well, I take a giant ruler and I draw a line on the ground. I then stand across the line, close my eyes, throw all my money up in the air, and all the money that lands to the left of the line I keep, and all the money that lands to the right of the line I give to charity. Well, says the third mathematician, that's really quite interesting. What I do is I throw all my money up in the air, and whatever God takes is his, and whatever comes back down, I get to keep. I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.